How do you rotate a digital photo in place, with no extra space? Rotate image is a Pattern Mastery 100 favorite and a frequent question at Google, Amazon, and Facebook, designed to test your understanding of matrix manipulation. Over 35% of candidates either use extra space or get tangled in index math. Master this, and you'll ace matrix transformations in any interview. Let's break down rotate image using the basic approach, so you can confidently tackle any in-place matrix manipulation problem. Given an NXN 2D matrix representing an image, rotate the image by 90 degrees, clockwise, in place, i.e., don't use another matrix. Input. 2D list matrix, NXN integers output. The matrix is modified in place. Interviewer might ask, how would you rotate a digital image in place for real-time rendering? What's tricky? Must rotate in place, no extra space for another matrix. Need to move elements layer by layer, or use clever matrix transposition and row reversal. Index calculations for four-way swaps can trip you up. There are two classic approaches. Transpose and reverse. Transpose the matrix, swap rows and columns. Reverse each row. Layer by layer four-way swap. For each layer, move elements in groups of 4, rotating their positions. Let's clarify the transpose and reverse method. Transpose. For each cell, I, j, with I less than j, swap matrix ij, and matrix ji. Reverse. For each row, reverse its elements. Transpose the matrix. For I in 0 to n1. For j in I plus 1 to n1. Swap matrix ij, and matrix ji reverse each row. For each row in matrix. Reverse row in place. We start by defining our solution class. This class will contain the method that rotates a square matrix by 90 degrees clockwise. This is our rotate method, which takes a 2D matrix and rotates it in place, meaning we don't create a new matrix, we modify the existing one directly. We store the size of the matrix in n. Because the matrix is square, n represents both the number of rows and columns. This comment explains the first step, transposing the matrix. Transposing means flipping the matrix over its diagonal, like reflecting it across a mirror from the top left to bottom right. We start a loop over the rows. The variable I moves from 0 to n1. In this inner loop, j starts at I plus 1. This ensures we only swap elements above the diagonal with their symmetric counterparts below the diagonal, preventing double swapping. We temporarily store the value at position, I, j, so we don't lose it during the swap. We swap the element above the diagonal with the element symmetric to it below the diagonal. For example, 0, 2, swaps with 2, 0. And we finish the swap by placing the original value into its new position. This completes the transposition step for this pair. This closes the inner loop for column j. And this closes the outer loop for row I. At this point, the matrix has been fully transposed. Now we start the second step, reversing each row. After transposing, reversing each row produces a 90-degree clockwise rotation. We loop through each row I one by one. We set 2 pointers. Left starts at the beginning of the row. Right starts at the end. We'll swap these inward to reverse the row. This loop runs until the 2 pointers meet in the middle. At each iteration, we swap the elements at left and right. We temporarily store the left element so we don't lose it during the swap. We move the right element into the left position. And we move the original left element into the right position. Now the two values have swapped. We move the left pointer inward. And we move the right pointer inward as well. Next iteration will swap the next pair. This closes the while loop for reversing the current row. And this closes the loop for all rows. Now every row has been reversed, completing the rotation. This ends the rotate method. And this closes the entire solution class. Time complexity note. Transposing takes O(n) squared time because we visit half the matrix. Reversing every row also takes O(n) squared time because each row has n elements and there are n rows. Overall time complexity, O(n) squared space complexity, O(1). We do an in-place rotation. And that's how this algorithm works. It first flips the matrix over its diagonal to transpose it, then reverses each row to complete the rotation. Efficient, simple, and elegant. Let's run our function on this test case. This matrix represents a 3x3 image or grid. Row 1, 1, 2, 3. Row 2, 4, 5, 6. Row 3, 7, 8, 9. Our goal is to rotate this matrix 90 degrees clockwise in place. After a 90 degrees clockwise rotation, the original left column, 1, 4, 7, becomes the top row, but reversed, 7, 4, 1. The original middle column, 2, 5, 8, becomes the middle row, reversed, 8, 5, 2. The original right column, 3, 6, 9, becomes the bottom row, reversed, 9, 6, 3. 7, 4, 1, 8, 5, 2, 9, 6, 3. And that's exactly what our program produces. The output perfectly matches the expected rotated matrix. So, our implementation is correct. The algorithm successfully rotates the matrix 90 degrees clockwise in place, efficient and accurate. We begin by defining a class named solution, which stores our rotation method. This method rotates a square matrix 90 degrees clockwise in place, meaning no extra matrix is created. Everything is rearranged directly inside the existing grid. We store the dimension of the matrix in n. Since the matrix is n times n, this tells us how many rows and columns exist. A matrix can be imagined like an onion. It has layers. We rotate the outer layer first, then the layer inside it, and so on. This loop goes through each layer. I equals 0 outermost layer. I equals 1 next inner layer. We only need n/2 layers because rotating stops at the center. This inner loop moves along the current layer's top row, from left to right. Each j identifies a square in the top row that needs rotating. We temporarily store the top element in temp because it will be overwritten soon. Think of this as holding onto the top value before the rotation shifts everything. Here we move the left element into the top position. We're effectively pulling the cell from the left side of the same layer and placing it up top. Now the bottom element moves into the left position. This continues the rotation cycle clockwise. Next, the right element moves into the bottom position. Finally, the original top element, stored in temp, moves into the right position. This completes the rotation of the four corners for this particular square. Finished rotating all elements in the current layer's top row. Finished rotating all layers of the matrix. Closing the rotate method. Since the rotation is done in place, no return value is needed. Closing the class. And that's how this algorithm works. It first processes the matrix layer by layer, then rotates each group of 4 cells by cycling values around the edges. Efficient, simple, and elegant. Let's test our function using this input, a 4 times 4 matrix of numbers. This matrix represents a square image or grid that we want to rotate 90 degrees clockwise in place. Here's why the solution works. Our algorithm rearranges the elements so that each value moves to its correct rotated position. Conceptually, elements from the top row move to the rightmost column, the right column goes to the bottom row, and so on, layer by layer. For example, the top left value 5 moves to the top of the right column new position, 0, 3, becomes 5. The value 2, second row, first column, moves up into the second position of the right column. It appears as 2 in the first row of the rotated matrix. Similarly, the bottom left value 15 moves to the start of the top row of the rotated matrix. Doing this systematically for all elements gives us the new matrix. 15, 13, 2, 5, 14, 3, 4, 1, 12, 6, 8, 9, 16, 7, 10, 11. And that's exactly what our program outputs. 15, 13, 2, 5, 14, 3, 4, 1, 12, 6, 8, 9, 16, 7, 10, 11. This matches the expected result and confirms that every element has been rotated into the correct position. So, our implementation is correct. The algorithm successfully rotates the matrix 90 degrees clockwise in place, efficient, accurate, and reliable. So, let's wrap it up. The rotate image problem is one of those elegant matrix challenges that looks simple but quickly exposes whether you really understand in-place transformations. No shortcuts, no extra space. We started by restating the goal. Rotate an n by n matrix 90 degrees clockwise, directly in place. It's about repositioning every element exactly where it belongs, just like rotating a digital photo pixel by pixel, without creating a new copy. We compared 2 main strategies, the transpose and reverse method versus the layer by layer 4-way swap. Both work, but the transpose and reverse approach is simpler, cleaner, and easier to explain in interviews. The key challenge? Managing indices correctly while staying truly in place. Our plan was straightforward. First transpose the matrix by swapping rows and columns, then reverse each row to complete the 90 degrees rotation. 2 simple passes, 0 extra space. We followed that logic precisely, ran the code on LeetCode, and it executed successfully. No errors, no extra memory used. We verified the results, And every test case passed exactly as expected, confirming that our rotation logic holds up perfectly for all matrix sizes. The big takeaway? Mastering in-place transformations like this builds your confidence with array and matrix manipulation, a skill that's essential not just for interviews, but for real-world data and graphics processing challenges.